Okay, hello Nidir, long time. So, I thought we'll do just redox reaction today. We'll get into chemistry and we'll try to do chemistry through these lecture series. We'll then go to equilibrium and Redox reaction, but probably we won't be able to cover that today. So we'll just cover the basis of redox reaction today, right? Like basic, as in the whole chapter, right? Okay. Mm, so let's get started. Hopefully you can see things here. So we are going to do, yeah, so it is visible. So redox reactions today. Cool. So you have already, I think, done this at school, so this will be a quick revision. It's a fairly simple chapter. So we are just basically trying to understand two things, right? We're basically trying to understand oxidation, and then the other thing is we're trying to understand reduction, right? So sorry about that. Yeah. So the okay, yeah. So of course, so the first thing about how we define oxidation and reduction of in a reaction is we just say that if it gains oxygen, it is oxidation. If it loses oxygen, it is reduction, right? So that's the simplest thing that you can tell, right? So it is very simple. So something like Na plus O2 giving you Na2, right? So this is what? This is sodium oxide, right? So in this phase, this sodium did not have oxygen and now it does have oxygen with it, right? So we will say that this sodium is simply oxidized. Like simple. Okay. So let's take another example, right? Let's take a example in which things break down. Maybe you have a Cu2O and then you just heat it. It gives you Cu plus O2. Maybe it's a little unstable as a compound and you just heat it, it just breaks down, right? In this case, take a guess what this would be. It had oxygen before and it lost oxygen, of course, then it will be reduction. Right, so this is the simplest. So gain or loss of oxygen. Right, okay, that's fair and square, easy. But then we see that there are some reactions in which there is no oxygen. So how do we talk about that? Then we try to broaden our definition. We say that number two will be maybe it loses hydrogen and gains hydrogen. Right, the opposite. So let's look at a couple more examples. Right. So for this thing, it's loss slash gain of hydrogen. We will maybe we'll and now we can also talk about reactions like hydride formation reactions, right? Which is say maybe Na plus H2 giving you NaH, right? So we have sodium hydrides, right? Of course, this is not balanced and to balance them, but yeah, this is good. So we can call them sodium hydride reactions. So hydride formation reactions, right? So something like this now it will, even though it is gaining hydrogen, we will just say that this is reduction now, right? Broadly. Or one common example would be maybe you have an alkene and then you have adding hydrogen. Take a guess what it would be. Right, it should be hydro. This should form alkane, and these reactions we call them hydrogenation reactions, right? So alkene, which is a double bond, an unsaturated compound going into a saturated compound, which is a single bond, right? Something like this would be what? Reduction, right? And similarly, dehydrogenation. Remember that this is different from dehydration, which was water. This is hydrogen. Dehydrogenation will be an example of oxidation reaction. Okay, fair and square. We have broadened our definition of oxidation and reduction to maybe include more things. Let's broaden it now even more. Right now, we talk about um, oxidation will be losing electrons, and reduction will be gaining electrons, right? So, again, we are continuing to broaden our definition. Now we have gotten to a point where we are talking about electrons now, right? So now we're talking about gain or loss of electrons. So when we talk about electrons, then we can start talking about ions because electrons have charge, and when electrons will be lost or gained, then you'll have charge that is coming in and going, right? So let's talk about maybe just something like sodium that can maybe lose an electron, right? It can lose an electron and then give you Na plus, right? Fairly common reaction, as you know that this is in the, so if this is the periodic table, then these two, group 1 and group 2, want to lose electrons, right? And then these 7, 8, and somewhere maybe even like 6 want to gain electrons, right? We know this. Yeah, like I'm just, this is not really accurate. It should be, you know how to draw a periodic table anyway. We know that these people want to lose electrons, so Na here will want to lose electron and then form Na plus, right? So generally we write this reaction like this. So an electron is kind of given out in a way, which is the same thing as the top reaction. It says it has lost an electron. The other thing is just saying that it is giving out an electron, which is the same thing. So in this case, we see that from here to here will be, take a guess, will be oxidation or reduction. This will be oxidation. So it is losing electrons, so it is oxidation, right? And this Na lost electrons. One Na atom is giving out one electron to form one Na ion, right? This is an ion, this is a stable atom, okay? And then we are also, of course, giving out electrons, right? So, and then if you think about the other end of the spectrum, group 7, group 8, then you start thinking about maybe things like chlorine, right? So chlorine will always gain electrons and form chlorine minus, something like that. It has 7 electrons in its valence shell. It wants to gain one to get an octet of 8, which will make it stable and happy with a complete octet. So it will be happy. So it forms an ion here. You go from a stable atom, and this single atom has gained electrons, so this itself will be reduced, right? So this is a very broad thing. Now we'll see. So now this definition also includes ions, right? So we continue to broaden our definitions. The first thing, just to recap, first thing we talked about was oxygen. We covered some oxidation burning reactions right here, burning and heating decomposition reactions here. Then we added H2, then we can convert it, talk about hydrogenation, hydride formations, hydrogenation, dehydrogenation reactions. And then we have talked about generally now formation of ions, right? Let's continue again, just to show things to you from the book. We are just covering things according to your book itself. So we'll continue to cover that. You can always use a book as a reference. Okay. Now, something curious happens when we define oxidation and reduction in terms of electron change. Let's look at what that is. So, say you write a reaction, which is, let's take the one given in your book, maybe NaCl. Let me look at the reaction. Yeah, so it's the formation of NaCl reaction, right? So NaCl is being formed, and it will be formed when sodium and chlorine react. Now chlorine, of course, is that as a gas. It is Cl2, and Na is a metal, so in natural forming state will be Na, right? So, and then you form it into this kind of reaction. You balance it first. Now we are good. So this is forming sodium chloride. Now if you look at this reaction, we can write something called a half equation. When we are looking at a half equation, we say that, okay, maybe I can say that each Na molecule uh, became Na plus, and then each one of this molecule ka every atom broke down to form a 2Cl minus right here. So why do we call it half equation? So we can see that maybe this guy sodium here was a stable atom before, and then it formed an ion. So both of them went from atoms to ions if you look at it in this way. And now we can relate to maybe what is oxidized and what is this thing. So later recall how we said that when atom gains an electron, it is reduced, which happens right here. Each of the atom in this molecule of chlorine has gained an electron to form Cl minus, and two ions of Cl minus are formed. So here there is reduction, and similarly there were two atoms of Na. Each of them have lost an electron right here and formed this. So similarly, let's also complete this. So we have two electrons that are coming in here. And this one is of course oxidized. Right? When we start looking at things this way, it looks like we can understand a reaction in terms of its half equations, and then half equations will tell us what is oxidized and what is reduced. So one curious observation that we have in this is, in this formation of NaCl, both oxidation and reduction has happened. This has also happened and this has also happened. These are generally called redox reactions, which is what the name of the chapter is, meaning reduction and oxidation, right? So the idea is that whenever a reaction happens, oxidation and reduction always happen in pairs. So in our case, sodium was oxidized and chlorine was reduced, and which is what is generally seen. One atom is oxidized, or one molecule is generally oxidized, and another molecule is reduced. Now, throughout the rest of the chapter, we'll just see examples of this and how to identify which atoms are reduced and which atoms are oxidized. So, this will be our work in the rest of the chapter now. So okay, great. Now, if we come back to our broader definition, we have seen that defining three has actually made our life a lot more broad. Like we can analyze a lot more reactions. We are just not looking at these oxidation or hydride formation reaction. We can look at now all kinds of reactions. As long as we can write half equations of them, we are good. So let's try to see some half reactions here. Okay. So one of the things that these people talk about here is construct a balanced, okay, balanced, yeah, fine. So construct a balanced ionic equation of the reaction between nickel and iron 3 ions. So this 3 is of course the oxidation state, or like the valency of the iron atom. So it's already given to us. So this is reacting with stable nickel atom. So this is an atom, this is an ion. So an ion and an atom is reacting, and then we need to know what is formed. So half equations are already given to us. So this is the half equation for nickel, and this is the half equation for iron. We can see that there is two electrons that nickel has to lose to form an ion, and iron has to gain an electron to form a lower uh, an altered version of carbon, right? Okay. Okay. So let's see. So they are telling us we are going now the other way. Normally we were given a reaction, and then we would break it down into um, half equations, and then we would try to understand which one is reacted, which one is oxidized. Here they have already told us that nickel here is oxidized because it has lost electrons, and iron here is reduced, right? And so that is already given to us. Now they're just telling us to go back to the main equation. So let's just try to multiply this equation in such a way that the electrons there get cancelled on both sides. So the exchange should be same in terms of electrons. So what we do is we just multiply this equation by 2. So you have 2Fe, 2, it's like it's solving two linear equations that we do in math, right? We multiply this by 2 and then add them. So this is exactly what we're doing here. We multiply this by 2 and try to add them. So we have an equation like this with no electrons, right? So something like this, we are here, we can talk about that. Okay, nickel here is oxidized and iron here is reduced. Okay, easy enough. And let's keep going. So definitely, for this chapter, you should literally practice every example and every question that's there. It will not be very complicated, but you need this practice, and you can just go through that very quickly. So whatever I'm not discussing here, do attempt it uh, in your time. So let's try to look at another question. Construct the balanced ionic equation for the reaction of iodide ions with manganate ions in the presence of hydrogen ions. Use the following two half equations to help you. So again, similar question, we are given two half equations. Again, although more complicated, but they're still half equations, and then they're trying to give us the ionic. And they're telling us to get the balanced ionic equation. So let's look at it. So the idea is we have to make these electrons same. So we have to multiply this by some number and this by some number and then add them such that the electrons get cancelled. So try to attempt this on your own and then try to see that if we get this as the answer. Okay, fair enough. So now let's look at, let's keep moving. So now let's try to make our life a little bit simpler and define something. So define a fourth rule here, which will make our life a little bit simpler. And we'll just say that oxidation and when, let's try to write it. So oxidation is when oxidation number, whatever this is, increases, and reduction is when oxidation number decreases, right? So this will be the simplest definition that we'll try to use everywhere. So the idea is every atom, every ion will be assigned a oxidation number on both sides of the reactions. So we will see that on the left hand side, on the reactant side, what is the oxidation number, and on the product side, what is the oxidation number. And if that oxidation number has changed, that means that there has been some oxidation or reduction, and we'll see whoever atoms oxidation number has gone up, that means it has oxidized, and the other one has gone reduced, right? So we'll talk about those ones now. Okay, so let's go through it slowly. So first of all, before we get into change of oxidation number, we need to first understand what oxidation number is, right? So there are a few basic 6 rules. So let's look at that. It's very simple. Once you start to understand it, you don't even have to remember these rules. They go straight into your head. So let's look at what the rules are. So the rule number 1, oxidation number of any pure element, any uncombined element is always 0. So something like a chlorine gas, Cl2, something like a zinc, something like a sodium, Na, everything in its basic form is 0. So sulfur combines in S8, so that all S's have a oxidation number of 0. Okay, fair enough. Second one, we say that some elements, some atoms, some ions have a fixed oxidation number. So fluorine will always be -1, oxygen will always be -2, hydrogen will always be +1, Group 1 are always plus 1, group 2 are always plus 2. So 5 rules, remember them. Oxygen minus 2, hydrogen plus 1, except there is a hydride exception. For metal hydride, it is minus 1, but it is generally always plus 1. Uh, Fluorine is always minus 1. Group 1 and 2 are always plus 1 and plus 2 respectively. Okay. And here oxygen is minus 2 except in peroxides. Peroxides we'll talk about separately. Okay, cool. Okay, so let's keep going. Then the next thing that you talk about, next rule is oxidation number is the same as the charge. So if this is Cl minus, which is an ion, then in this case, this Cl's oxidation number is minus 1. See, this was an atom, then this Cl's oxidation number, each Cl's oxidation number is 0, 0 and 0, and total is also 0. In this one, there is only one Cl, and that is in the ionic form, whose oxidation number is minus 1. So oxidation number can be positive, 0 or negative. Okay, similarly, Al3 plus has a charge of plus 3, so oxidation number is also plus 3. So this rule is specifically only for ions. Okay, so let's keep going. Then they say that just like a pure element, the oxidation number is 0. Here they're saying if there is a compound, then whoever is there, then sum of their oxidation numbers must be 0, must be stable, 0. Okay, if it is an ion with many atoms, then sum of oxidation number should be same as the charge. Okay, this one was a monoatomic ion, which is just pure one ion like Cl minus Na plus. This is a complicated ion like NO3 minus, sulfate, nitrate, right? So in that case, the sum of all the atoms will be equal to the charge. Sum of the oxidation number of all the atoms will be equal to the charge. Okay, and the last one, which is this is the most helpful, is the most electronegative element has the negative oxidation number. Okay, so we'll see how these rules check apply. So let's keep going. You will commit them to memory very soon. So let's look at this guy, Na2O, right? So we know that Na2O here. What are the oxidation number of Na and O? So let's try to do that. So we are going to do oxidation number. The first example that we look at is Na2O. So in this case, the first thing that we say is few things have fixed oxidation number. So we know that oxygen always has a oxidation number of -2, right? So oxygen has a oxidation number of -2. Na, we don't know what is the oxidation number. So what we can do is we can say maybe the oxidation number is X. Then each atom of Na has X. So that means 2 into X is the Na contribution. And then you have 1 which is contributing -2, which is from O. And then the sum of this, because it's a compound, it must be equal to 0. Right? So you can solve this to get X equal to +1. Which also checks out with our original this thing that group 1 elements should have a thing of +1. Okay, feel free to rewind and recheck the facts, but keep following. So let's keep going. So this is a metal non-metal. Okay, so let's keep going now. A metal non-metal. Now let's look at Na2S. We'll follow your book. So in this case, how do we say which one is what? So in this case, okay. So in this case, let's now say that, okay, we don't know of either, but then one of them is a group 1 element, right? Which one is group 1? Na is, right? So Na will say that this is +1, and then S maybe we don't know that it is X. So here the same thing. So with two atoms of Na each having a +1, and then S you have a minus. S you don't know, right? So and then you get X equal to -2. So here S will be -2. So let's keep going. Let's look at some now non-metal ones. So maybe SO2. Okay, so the most electronegative element, there are both electronegative, but most electronegative is oxygen amongst these two. So oxygen will have a -2 charge, -2 oxidation number. What is the oxidation number of S here? Again, if we assume as X, then X minus 2 times -2, sorry, X plus 2 times -2 will be equal to 0, then X is equal to 4. Here. So you can see that here in this case, this S has an oxidation number of -2, and this S has an oxidation number of +4 here. So the same element can have different oxidation number and it's combined differently, right? So let's keep going. So sodium chloride, iodine chloride. So now this is a tricky one, right? So first thing that we need to do is identify which. So now in this case, both are second last group, the halogen group, right? So we need to understand that which one of them is more electronegative. So in this case, chlorine is more electronegative, and you should remember that from the periodic table that as you go down in one group, then electronegativity decreases. So this is the most electronegative, and then this is the least electronegative, and then in the middle is maybe somewhere in the middle, right? So the order goes fluorine, chlorine, bromine, and iodine. So this is iodine at the bottom and then chlorine at the top. So chlorine will have a higher electronegativity. So chlorine will be -1. And then let's try to figure out what is of iodine. Take a guess. Right. So it should be +3 right here. Right. So now we know that we have a rough idea about how to find. In hydrazine, again, now this is complicated, but you must assume that hydrogen has +1. So nitrogen you will get as -2. Okay. So this is fair enough. Okay, what about an ion? Let's try for an ion now. So maybe NO3 minus, right? So this ion is now overall has a negative charge. So we need to now deal with this carefully. For this nitrogen, we don't know what is the oxidation number. For oxygen, we know that it is -2. So now in this case, we'll write the equation as X plus -2 times 3. Now in this case won't be equal to 0, but will be equal to -1, which will be the charge. So you can simplify this to find that X is equal to 5 right here. Right, so the oxidation number of nitrogen in ion, nitrate ion, right, is +5. Fine, fair enough. If you're following this, try to definitely attempt all of these. They're fairly easy, but you need to know how to do them because as we go around, it will be helpful. Okay, so now that we know how to find oxidation numbers, let's look at a redox reaction, which we were talking about, right? We said that if the oxidation number increases of an atom, then it is oxidation. If the oxidation number reduces, then it's reduction, right? Simple. So something like this. So if you have a reaction like this, where you have Sn, so it's a pure element which is tin. So this tin has an oxidation number of 0. It makes SnO2. So in this case, if you find that oxidation number of Sn will be +4, you can try doing that. Oxygen is -2, some should be 0 because it is stable. So Sn is +4. And then in this case, H is +1, O is -2, and it is stable, so it should somehow come out to be 0. So this will come out to be +5 right here of nitrogen. And here nitrogen oxidation number, which we have already found, NO2, is +4 here. So we can see that N has reduced in oxidation number and this has increased. So we can say that this is oxidation and this is reduced. In other words, tin is oxidized and nitric acid is reduced. As we said, one oxidizes and one reduces. Okay. Another way to say it is because this is oxidized, tin is oxidized, we can say the nitric acid acted as a oxidizing agent for tin. So what is oxidized here? Tin. Who is the oxidizing agent? Nitric acid. Again, opposite is also true. Who is reduced? Nitric acid. Who was the reducing agent? Tin. It caused the reduction to happen. So reducing agent themselves are oxidized, but they reduced the other guy. Okay, fair enough. If you understand this, then we are good, which is what this talks about here. You should definitely try to understand what is happening here, but then the concept remains the same. Okay, so the idea is now we can just look at the reaction and try to just calculate the oxidation numbers on all sides. And by looking at the oxidation and the change in oxidation number, we can say that whether it's oxidation or reduction, that particular half reaction, so to speak, like this is one half of the reaction, this is the other half of the reaction. So we can also see that there are things like H2O which do not take part in this, and which is fine. They are not oxidized or reduced, and that's okay. Okay, as long as we are good on that, that is cool. Okay, then a couple last things that we talked about. Now these are all. If you understand this, then this is the core of the chapter. Now we're just going to talk about things around it. So the first thing that we talk about is naming of compounds. So sometimes what you see is compound names like this: nitrogen oxide, nitrogen oxide, nitrogen oxide. But these numbers are changing. Now these are the same as oxidation numbers, and you can see that this nitrogen oxide has a formula of N2O, this nitrogen oxide has a formula of NO, and this nitrogen oxide has a formula of NO2. Now if you try to find the oxidation number of nitrogen in all of these three, so this one has an oxidation number of plus 2, right? So because oxygen has minus 2, so this must be plus 2, which is why it says 2 here. Because nitrogen is in the second oxidation state. In this case, this is minus 2 and nitrogen should be 2 times x minus 2 equal to 0. That will give you x equal to plus 1. So it's in the oxidation state of 1. And similarly, here is the oxidation state of plus 4. So this is why, so you can name compounds this way. So that nitrogen 2 oxide, nitrogen 4 oxide, that completely describes what kind of an oxide you're looking at. Okay, similarly, you can talk about iron 2 chloride and iron 3 chloride, and the formula will be FeCl3 and FeCl2, depending on what the name is, right? Okay, similarly, you can talk about sodium nitrate 3, sodium nitrate 5, in which nitrogen is changing oxidation number depending on it is NaNO or NaNO3. You will learn to do all of this, just go through what the book is talking about. Definitely, again, look at all of them and try to give them names with numbers here. Okay, if you understand that, that's the first thing. From name to formula, formula to name, you should be able to do both conversions. So iron 3 oxide should be FeCl3, because that will give you an oxidation number of plus 3 to the carbon. You should definitely try to do them. Phosphorus chloride should be P. It can be again no, because it has to be plus 3, so it can be PCl5 or PCl3. But it is because it is 3, then should be PCl3. You should definitely attempt these on your own as well and try to work them. Once you get good at it, you can do them in your head. But again, practice is important. Okay, last two things that we're going to talk about is you can balance equations uh, with using oxidation number. We have already kind of looked at it when we made the electrons equal and then we cancelled out those on both sides. So the similar thing that we'll do here. Let's see an example. So we have an unbalanced equation first, right? We try to find oxidation numbers of all of them. So oxygen is minus 2, so copper will be plus 2. Here hydrogen is plus 1, so nitrogen is minus 3. This is an element, so it is copper is 0, and this is an element, so copper is 0, nitrogen is 0. Here this is 2 and minus 2. We see that, okay, now we look at all of these oxidation numbers, we see what has reduced and what has changed. So we see that hydrogen has not changed. We see that oxygen has not changed. But we see that this nitrogen has gone from minus 3 to 0. That means it is oxidized itself. And here copper has gone from plus 2 to 0. So copper itself has reduced. Right? So we write it something like this. So oxidation change here is minus 2, meaning that it has kind of gained 2 electrons. And here the oxidation state is plus 3. So it means it has lost 3 electrons. Now we want to make those electrons or the oxidation change in oxidation number same. So we'll multiply these by 3. So that total change of oxidation number is 6, and we'll multiply the upper side by 2. So means that we'll put a 2 and 2 here, right, and a 3 and 3 here, right? So that makes an oxidation. So now that sets the oxidation number change as same. So now the second thing that you try to do is try to balance charges, but charges you don't have to balance. We'll come to that later. So now the next thing that you do is just balance everything else that is not balanced. So like H2 here is still not balanced. So you just look at, okay, how many hydrogens are there? 6, and here you have only 2. So now you can add 3 times this, and then this will complete your reaction. Right, so let's look at it again. You try to write the unbalanced equation. You try to write all the oxidation numbers for it. You see how much is the change. You try to make the change equal by adding a suitable factor on either side, right? And then then those ratios are fixed. Then you try to balance whatever is left outside, right? So they have given one more example. Definitely go through that and definitely try this. Okay. And the last thing that we are going to talk about is this weird corner case, which is the case of disproportionation. Okay, chemistry has weird names. I can't help it, but yeah. Okay, so disproportionation is when one atom, one molecule, itself undergoes oxidation and reduction at the same time. So this happens in the case of chlorine. When you add chlorine to NaOH, if you calculate the oxidation numbers of all the atoms here, I highly encourage you to do that. Pause and just do that. You will see that one half of the reaction, one chlorine, goes from 0 here to -1 NaCl. So here it is reduced, right? But the other thing, you see that here Na is +1, then all Nas are still -1. All Nas are still +1. So this Na is not no, is not changing. This O is not changing. This H is not changing. So this actually does not participate in this process of oxidation and reduction. So we say that, okay, we have found what has reduced, but what has oxidized? So we find that this Cl is actually in a state of +1. So the same chlorine, half of the chlorine is reduced and half of the chlorine is oxidized. So we can say that it is a complicated reaction in which we need to have something like this. So half of chlorine is reduced and half of chlorine is oxidized to this guy, right? So this is a chlorate ion. Like we have a nitrate, a sulfate ion, we have a chlorate ion. In this, in which the oxidation state of chlorine is +1. So this is an interesting corner case where one same atom or same element is both reduced and oxidized at the same time. This is sometimes seen in chemistry, but yeah, you need to keep this in mind. Okay, so for a disproportionation kind of reaction, how do you do the balancing? It is pretty much the same. So you write the unbalanced equation first, right? And then you try to see what is the change of oxidation number. So one change was -1 and one change was +5. You try to write them in such a way that the oxidation numbers are now will be same. You try to add a multiplier factor. You see that the multiplier factor here is 5. So this upper equation needs to be multiplied by 5 to make the change same. So then this will become 5 by 2 Cl2, and then you'll have a Cl2 here. So when you add them, now the like terms will add up. So 5 by 2 plus 1 by 2 will be equal to 3 total. So you have 3 Cl2 and rest everything else just crosses, just checks out. So 5 Cl comes from here, but then this is just single one, and then you have an OH minus which comes from here at the top. Okay, just try to follow this slowly, you will get, and then you add the non-participating atom also in the middle. So this will be our complete reaction, and after this you need to do now one more additional step, which is to balance the charges. So you see that, okay, on the left hand side you have a charge of -1, this is a charge of 0, this is a charge of -1, and then on the right hand side you have a charge of -5, and this is a charge of -1, so total of -6, and then this is just -1. So you multiply this by 6, to balance the charges first. And now this balancing of charges is done, and now you do the last step as before, which is to balance the non-participating atoms here, which is the H2O, right? And then you just try to see, okay, there are six H's here, you need to have six H's here, so you just balance them accordingly. So just to do all of these steps again, first you write the unbalanced, this is the whole equation, this is the unbalanced equation. You try to write both sides and try to see the oxidation number change. You try to make the oxidation change same. Then you try to balance the charges, which is just to see broadly on the left hand side, on the reactant side, how what is the charge, on the product side, what is the charge. And then you try to then finally balance the non-participating atoms, which is like the water and everything else. Definitely recommend you to try this. If there's any problem, then we can discuss. And that is pretty much it. So this is a basic idea of the redox reaction, which is a very important, easy concept in chemistry. It's almost like math in chemistry. It just flows. Just try to understand it. Try to do all of the questions inside the text, inside the chapter. I'm not giving you any end of the question chapters. Just try to do chapters that are internal to the book, and you should be good. Okay, I'll see you in some time. Next time we'll discuss the equilibrium. Awesome. Bye bye.